In this example, we will demonstrate the functionality of the Distance Protection Coordination Assistant. This tool is used to automatically calculate zone reach settings for distance protection relays. The settings which are calculated depend on the network topology as well as a set of rules for which the user can define parameters. Activate the study case number 5, Distance Protection Coordination Assistant. Here you can see the network that we will be working with. A 220 kV voltage level is shown in red and a 90 kV voltage level is shown in blue. We will be working with relays which have already been installed in the 90 kV network. We can show the locations of these relay models by changing the diagram colouring mode. Choose the option Secondary Equipment and Relays, Current and Voltage Transformers. Select OK. The location of the relays is shown in red on the diagram. We can take a closer look at the relay models installed in the network by right-clicking on a cubicle and choosing the option Edit Devices. Here, contained within the cubicle, you can see that there is a relay model, a current transformer model, a voltage transformer model, and 3 switching elements. Double-click on the relay model to take a closer look at its settings. Here you can see the Elm relay object. Within this object, all the settings of the relay are defined. In this example, some of the settings have already been defined. These settings are not calculated by the Distance Protection Coordination Assistant. The Distance Protection Coordination Assistant focuses on the zone reach settings, as well as the associated time delays. For this particular relay type, time delays are assigned using the illustrated blocks. Phase-to-phase element settings are calculated, as well as phase-to-earth element settings. In addition, overreach zone settings may be calculated, although in this particular case there is no overreach zone in the relay. Select OK to return to the network. As well as relays, there are a number of paths which have been defined in this network already. We can change the colouring mode again to show the location of the paths. Choose the option Groupings, and then choose the option Paths. You can see that 3 paths have been defined. One is red, one is green, and one is pink. Select OK. Here you can see the paths. Paths are used to define coordination paths along which the coordination of the different relay elements can be examined. The Distance Protection Coordination Assistant can be provided with these paths and can automatically calculate the zone reach settings for each of the elements contained within that path. Let's start the Distance Protection Coordination Assistant. Make sure that the toolbox is selected to the Protection toolbox. Then choose the Protection Coordination Assistant icon. First, we must tell the Coordination Assistant which part of the network we wish to coordinate. This can be done by selecting the paths that you wish to coordinate. Choose the option here, Select Paths. These are the 3 paths we already have defined. Multi-select those paths and select OK. You do not necessarily need to have already defined protection devices in your network in order to use the assistant. If you choose the option according to network topology, the tool will simply assume the locations of the relay devices in the networks, given the structure of the paths you have provided the tool. In our case, we actually have protection devices installed in the network, so we will choose the second option. Choose the distance protection page. On this page, we define the rules which will be used to calculate the reach settings of the distance relays. 3 different calculation methods have been incorporated into the tool for calculating reach settings. You can find descriptions of these calculation methods in the user manual. You can easily access the user manual by pressing the F1 key. If the Coordination Assistant has already been opened, then the user manual should jump to the appropriate part of the manual. Let's take a look at the equations which govern the settings rules for the different calculation methods. Here you can see the independent method. ZM1, ZM2 and ZM3 represent network impedances. ZF1, ZF2 and ZF3 represent zone factor settings. The zone factor settings are defined by the user in the coordination assistant. The calculated reach is ZS1 for zone 1, ZS2 for zone 2 and ZS3 for zone 3. You can see that there is a special consideration for parallel lines as well. Let's look at the second method, the cumulative method. Here you can see that only one zone factor is specified. For the second zone it is squared, for the third zone it is cubed. You can also see that the second zone calculation depends on the result of the first zone calculation, and likewise the third on the second zone calculation. Again, special consideration is given to parallel lines. The third and final method is known as the referred to line 1 method. Here you can see that all the zone reach settings depend on the impedance of the first line. Different zone factors are applied for each zone calculation. In our example, we will first use the cumulative method. We will apply the factors to the reactance. For the zone factors, we will use the default setting of 85% and an overreach zone setting of 120%. For the resistive reach of the relay, we will assume a fault resistance of 5 ohms, a factor for the phase-to-phase resistance of 0.5, and a factor for the phase-to-earth resistance of 1. Our timer settings will be 0 seconds for zone 1, 350 milliseconds for zone 2, and 700 milliseconds for zone 3. There is also an advanced option for the calculation of zone 3. This option determines whether the assistant tends to limit zone 3 to the second impedance or to an impedance beyond the second impedance. Leave it with the default setting and choose the option Execute. In the background, the Protection Coordination Assistant calculates the zone settings. We can view the results of the calculation by pressing the Output of Coordination Result button. Here we have 3 options. We can create a tabular report, we can create a time distance diagram, or we can choose to write back any results that we calculate to the protection devices which are installed. This option can only be used if you have actually installed protection devices in your network. First, let's create a report as well as to create the time distance diagrams. Choose the option Create Time Distance Diagram. Press the Execute button. Here you can see a tabular report detailing the settings as calculated by the assistant. The settings are presented per path defined. Here we are showing the calculated settings for the path S5 to S11. We can show different paths by choosing from the drop-down menu. Let's take a look at the settings in more detail. For the relay installed at the 90 kV substation 8 in the branch S8 to S9, you can see that settings have been defined for 3 main zones and an overreach zone. Reactance, resistance, earth resistance, impedance, angle, and time settings have been calculated. You can see that the time settings clearly follow the rules that were specified in the assistant. You can see that the reach setting of zone 1 is less than the reach setting of zone 2, which is less than the reach setting of zone 3. This is true for all cases. If you want to, you can try to manually calculate these settings based on the rules defined in the manual. If you want to export these results to spreadsheet format or HTML, then press the button in the top right-hand corner as illustrated. Now let's take a look at the coordination diagrams. You can see that 3 time distance coordination diagrams have been created. Let's focus on the time distance coordination diagram for path S8 to S11. The time distance coordination diagram illustrates distance along the x-axis and tripping time along the y-axis. The upper diagram illustrates the tripping time for power flows from the left of the diagram towards the right of the diagram, i.e. from busbar 8 in the direction of busbar 11. The lower diagram illustrates tripping times for power flows from the right-hand side of the diagram towards the left-hand side of the diagram, i.e. from substation 11 towards substation 8. Focusing on the upper diagram, let's consider what will happen for a fault 50% along the conductor between substation 10 and substation 11. Here, you can see that the relay installed at substation 10, located in the branch heading towards substation 11, will trip instantaneously. You can see that backup protection is also provided by the relays installed at substation 9, tripping time 350 milliseconds, and substation 8 with a tripping time of 700 milliseconds. You can see that for the reverse direction, i.e. the bottom diagram, that for a fault in the same location, the relay installed at substation 11 will also trip instantaneously. This indicates that for a fault on this particular location in the system will be selectively cleared in a very fast operating time, provided that the protection operates correctly. Focusing on the reverse direction again, you can see that there is a problem. You can see that the zone 2 and 3 reach of the relay at substation 11 does not extend the full length of the line. This problem is caused because of the mismatch between the lengths of the first line and the second two lines. The first line is much longer than the second two lines. This causes a problem when using this particular zone calculation method. In this case, the cumulative method is not necessarily the best method to use to calculate the settings. Let's try a different method. Choose the Protection Coordination Assistant button again. And let's choose the independent method. Apply the factors this time to the impedance. Use the default settings, 85%, 60% and 20%, and an overreach zone setting of 120%. Use the same time settings again. Select the Execute button. Here we can see the zone reach settings have changed. In this case, zone 2 and zone 3 now reach beyond the end of the long line. You can see that zone 2 and zone 3 are also providing some degree of backup protection for the lines between substation 10 and substation 9 and substation 9 and substation 8. In this case, you can see that there's definitely an improvement with regards to the settings. Now that we're happy with the settings that have been calculated, let's write these settings back to the installed protection devices. Press the Output of Coordination Result button again. And now choose the option Write Back to Protection Devices. Deselect the other options if you don't want them to appear. Select Execute. Here it is saying that settings will be written to protection devices and it is recommended to activate a variation. We will take this advice on board and create a variation. Choose No and select the option Insert Variation. Name the variation Distance Settings or similar and select OK. Choose to activate the new variation and name the expansion stage as well. Choose to set the new expansion stage as the recording expansion stage. Choose the option again, Output of Coordination Results, and select Execute. This time select Yes. The settings have now been written back to the protection devices installed in the network. The time distance diagrams illustrated are ideal time distance diagrams. They do not take into account the influence of other relay settings and other issues introduced by the network topology. Now that we've written the settings back to the devices, let's see what the real performance of the relays will be under short circuit calculation conditions. Double click on the diagram and change the method from coordination results to short circuit sweep. With the short circuit sweep method selected, a new calculation will be carried out in the time distance diagram where short circuits will be applied at intervals along the length of the path and the actual tripping time of the relays will be calculated. Let's carry out the short circuit calculations. Press this button, Short Circuit Calculation. We're going to carry out a short circuit calculation in accordance with the complete method. We're going to carry out a three-phase short circuit at each location in the path, and we're going to calculate maximum short circuit currents. Select Execute, and in the background you can see that the short circuit calculation has been carried out. Select OK. Here you can see the time distance diagram for the path, taking account of the real settings that have been applied to the relays. These diagrams could be further adjusted by altering the starting block settings for the respective relays.